Hello everyone. I think we'd like to get started. So welcome to tonight. We're very excited about tonight's speaker. Before we get there, I've got a couple of announcements to make. First of all, happy birthday to Valentina Tereshkova, first woman in space. It's her birthday today. She's 80-something and still looks like she could probably mop the floor with most of us. So lots of things going on. Obviously, we're coming up for the Apollo 11 anniversary in July. So we're trying to do a bunch of different things related to that as part of this program, but also within the Rice Space Institute. And there's a huge number of activities going on with Johnson Space Center and so on. So keep your eye out for that. What I did want to make an announcement of, some of you who are on our mailing list will see this, hopefully tomorrow or Friday. If you're not on our mailing list, please be on it. You can go to spacefrontiers.rice.edu and just put yourself on our mailing list. All you ever hear about are the talks. We don't solicit anything else. We don't send you nonsense, I hope. But one of our illustrious alumni, or at least actually former professors, had an experiment on Apollo 11. And there was only, I think, three Rice alum who had experiments on the Apollo, or by anybody who's, Brian O'Brien is the only one who's still alive. He's going to be in town for some other reasons next week. But on Monday, March 18 at 4 p.m., so it's going to be a late afternoon talk, he's going to talk to us about 60 years of studying the moon from the dust experiments he did way back in the Apollo days, all the way through to the Chinese missions that have gone recently. So we're really excited about that. The announcements will be coming out, hopefully through the email channels, on our website, through various means in the next week or two. Our next lecture in the Spaceport lectures will be on April 4th. And it will be George Abbey, who some of you may have been at his book signing the other night. There's a biography of George just come out called The Astronaut Maker. George is a space policy fellow at the Baker Institute here at Rice. Been there, done that. So he's going to be giving a talk, 50-year recollections of the Apollo program, April 4th. I think we're in this room. I don't know if Janice's here to confirm that. We're either here or we'll be over in Herring Hall, the usual time, 6:30 reception, 7 o'clock talk. So all those announcements will be coming out later too. And so now tonight's speaker, someone I've known for a little while. And before, I'd like to thank Arturo, finally made it. So Arturo, if you wouldn't mind standing up. I keep mentioning this is our sponsor, the Houston Spaceport. Arturo. Arturo's the general manager of Ellington Field, and I think I won't get in trouble by saying there might be some really exciting announcements coming out in the next couple of weeks, so keep your ears open for that. Nikki Fox. So Nikki, one of the things I like to, before I get into her formal NASA, where it's all very serious thing, many years ago I created a thing called Solar Week, which was a set of educational activities to encourage middle school girls to participate in science. And as part of that, I asked a cohort of colleagues, female scientists, to participate in this so that they could converse with scientists, but people they could relate to. Nikki was in that first group. Most of the conversations with Nikki were nothing to do with science. It was about how cool she was, and how cool her car was. And if I remember right, it was a Z3, BMW Z3 convertible. Her little baby at the time, she's got a couple of babies of a different species at the moment. But that kind of relationship with how these young women, and actually some young men would communicate and interact with these scientists, and it just shows you how active she is in promoting science, doing science, and all these different things. And so it's been a great pleasure to know her for all that time. And now the boning part, she's so she's a very illustrious career. She's, all these things going for her. She's English, but sometimes you can't be perfect. She's a Luton fan.
What?
I thought you were Luton.
Liverpool.
Oh, Liverpool. I support Liverpool. Now, I thought you were a Luton person too, you know. Luton's, anyway, we'll talk football later. No, but Nikki is, you know, just recently, through all of her illustrious career, you know, she's been working on space missions for NASA. She's been working with colleagues from NASA, a lot of us around the room here too. And I guess it was only, was it August?
Yes.
August 2018, last year, she moved to headquarters. And so she's the heliophysics division director. Heliophysics is a word that NASA made up, but it really talks about how the sun interacts with the solar system and the system there. And, you know, she's never talked to me again. I can tell that.
Yeah.
But it's a very important area for all of us, a number of us here, and so Nikki's heading up that program at NASA, so be nice to her, but so she'll be nice to us. She went there from the Applied Physics Lab at Johns Hopkins University in Laurel, Maryland, where she was actually the chief scientist for the heliophysics section over there, and also for tonight, most importantly, she was the project scientist for the Parker Solar Probe. And I think I'm really excited to see this mission go after all these years, and to hear what's happening with it, and it's great to have Nikki here to do this. Lots of papers, lots of accolades, interesting educational background, Imperial College, Science and Technology in London, where she did her BS in physics, BSc really, right?
Yeah.
BSc in physics.
I try not to BS physics.
Right. She got an MSc, a Master of Science in Telematics and Satellite Communications from the University of Surrey, and then back to Imperial to do her PhD in Space and Atmospheric Physics. And for those of us who have known Nikki over the years, she's contributed so much to our field, to the science that we all kind of love, and to the public dissemination of it. And I think you'll really in for a treat tonight. So please join me in welcoming Nikki first.
All right, so despite being an English Liverpool fan, here I am. So I'm delighted to be here tonight. It is actually my favorite thing to talk about, which is the Parker Solar Probe mission, or the coolest, hottest mission under the sun. Please hashtag that if you're going to post it. And so I wanted to start off by just, telling you a little bit about this made-up word called heliophysics. And so it is indeed a made-up word. So we used to be called the Sun-Earth Connections Division, and there was a request that every division at NASA was described with one word. So astrophysics, planetary, Earth, Sun-Earth connections, too many words. And so it became a challenge to come up with exactly what term you could use to really describe everything under the sun. And so, a lot of people think that we're a new division. But in fact, I like to think of us as the oldest division, in fact, the oldest branch of science, anything that's governed by the sun. Anyone who's seen a total solar eclipse knows the beautiful majesty of what goes on with our sun. And the sun captivated people's imagination. It fueled legends. It fueled myths. It fueled superstitions as to, suddenly you see this, the sun is doing this, therefore we're going to have a good harvest. Maybe the sun is doing something else, and we're going to have a bad harvest. And so the sun has always captivated and fascinated us. And so I think heliophysics is actually the original science discipline. Somebody asked me the other day how, so what is it that you control? And I said, well, I feel a bit like the Lion King. It's everything the light touches. It's right out to the very edge of our heliosphere. And so, of course, I'm going to talk to you about the very inside of our solar system, the sun. And so, David mentioned several things that went on 60 years ago. Well, actually, 61 years ago now, you will recognize James Van Allen, who had just launched Explorer 1, and of course made our first discovery of the space age, which was the Van Allen radiation belts. Also in 1958, a young scientist by the name of Eugene Parker published a paper. And this paper was so revolutionary and so interesting and so different, he basically predicted that there would be a solar wind, that the outer atmosphere of the sun will be continually accelerated and stream away, bathing all of the planets. Now, as with all good work, people didn't believe it. So he had a lot of trouble actually getting his paper published. 2 of the 3 reviewers thought it was really terrible. And in fact, one of them even commented, if you're going to publish in this type of area, you probably should visit a library first. Fortunately, and Jean thinks, I think it's one of Jean's favorite stories, but fortunately, the editor of the journal said, you know what, if it's causing this much controversy in the reviewing community, let's put it out there and see what happens. And so, of course, out it went in 1958. At the same time, in 1958, there was a commission that was chartered to really give guidance and advice to the newly forming agencies. So NASA is one, the National Science Foundation, and of course the DoD, the Department of Defense. We've discovered space isn't empty. We've discovered radiation. Now, what do we want to do with this newfound thing called space? And so they got together and they came up with these sort of big transformational missions that required more than just one institution, that required a big infrastructure, a big agency to be able to do these huge, groundbreaking science missions. Of those missions, the last one to fly has been a solar probe, not because people weren't interested, but just because we've had to wait that long for technology to catch up with our dreams. And so when we look at our sun, it's extremely beautiful, very, very dynamic, anything but constant. So, you know, when you hear people say, oh, it's as constant as the sun rising, there's really nothing constant about the sun. And so what you're looking at here is a very beautiful image taken by SDO of all these wonderful active regions. And we get very excited about the active regions, particularly when they throw off coronal mass ejections like you just saw. But of course, what we do know is that the solar wind is continually streaming, and therefore we sort of lie in that solar wind plasma. Anything that happens on the sun is going to be felt here at Earth. But this particular region around the sun is also the home of many mysteries. We've known about these mysteries for a long time. In fact, as long as we've been able to really look at the sun with scientific instruments and make these measurements, we've known that these mysteries exist. So the first one, and this is a nice sequence of images taken at different temperatures, and you'll see the temperature in the bottom of the plot there. And so this temperature is basically corresponding to distances away from the sun. And so we start at 6,000 degrees, and as we move away from the sun and we start taking these images, we see the corona further and further away from the sun. And so as we move away from the surface of the sun, instead of getting cooler, as you would if you walked away from a bonfire, the plasma itself in the corona is about 300 times hotter than the surface of the sun. And that just really shouldn't happen. It's like water flowing uphill. It's like, you know, dark matter. It shouldn't happen. Why does it happen? So our first mystery is the temperature rises as we move away from the surface. We call it the temperature inversion, and it is one of those things that has stumped scientists for decades. And every AGU, every one of our big conferences, you usually hear 2 or 3 new theories for why this is happening. And so far, not one of them has stood up to every single condition. So you have to put energy in. You have to keep putting the energy in. We can't explain why it happens. The other one, of course, is really the thing that Jean had predicted, which is that this atmosphere is continually streaming away. But it is more than just a quick burst of energy. It is continually accelerating as it moves away from the sun. If you just put some energy in the corona and you just let it sort of slow down, if you think about pumping the gas on a car and then just letting the car slow down, the solar wind doesn't do that. It is continually being accelerated. And so we can't explain that either. And so the second mystery is really, how is this solar wind continually accelerated? And so for decades and decades, we've wanted to answer this question. And the only way to really do it, we've looked at the sun in every different wavelength. We've made measurements in the solar wind, close to the Earth, and even in as far as the planet Mercury. But we've never been able to go up and really sample that plasma. And so the only way to answer these questions is to send a brave little spacecraft, it should be moving, into the solar wind. And this brave little spacecraft, I'm sure you'll be shocked to know, is Parker Solar Probe. And there is a particularly nice shot of Parker in all her glory, staring at the sun and taking our measurements. But of course, before we could actually get to this place, we had to do an awful lot of technology developments. And so I want to take a few minutes to talk about just the incredible engineering that goes into putting a spacecraft on or close up to the sun. So Parker Solar Probe was actually launched on the most powerful rocket available today to us, which is a Delta IV Heavy. Not only was it on a Delta IV, but it also had an upper stage, so it had a final kick motor. And yet, despite all this raw power sitting on the launch pad, we had to be extremely small and very compact, because we need to be thrown away from the Earth with so much energy that we actually lose all of the angular momentum or the effect of the angular momentum of the Earth. The Earth is moving very fast around the sun, and we do not want to be dragged around with the Earth. And so we had to move off with incredible launch energy to basically be able to turn this way and move in towards the sun. So the spacecraft herself is very small. She's about the size of a smart car. And she stands about 3 meters tall from stem to stern. That's with her heat shield on. At the widest part, of course, that is the heat shield, because that is providing the shade for the rest of the spacecraft. She is about 2.3 meters in diameter. And the spacecraft bus itself, so you see sort of the middle picture up there, that's just a shot of the outside of the structure. And that stands about 1.5 meters tall and 1 meter across. And when you consider everything that has to go inside that spacecraft, it is quite it's no small feat to pack that much stuff into this spacecraft. The bottom image you see there, it has the spacecraft harness in, and so that is all of the wiring and everything that is needed to be able to get the signals around the spacecraft. The reason I put that one in there, the pink, we do take the pink cover off before we launch, but that is the propulsion tank. And so there is no instruments, no subsystems. That is how crowded the spacecraft is before we've even put the important stuff in. And so it was quite a challenge. And we used to joke about, we needed very, very small integration and test people who could actually get in there. And we tried to find Oompa Loompas, for those of you who remember Willy Wonka. But we had to have very, very, very people that could really bend. And we actually ended up doing a virtual or an augmented reality system, a full-up virtual reality spacecraft, so the INT engineers could practice how they were going to do a lot of the integration. Because things like, where are you going to put your foot? Where is your arm going to be? What are you now impacting when you reach out here? Because it was so crowded to be able to actually put everything in the spacecraft. So, so that's what she looks like. That was our engineering design. The most important technological advancement we had to make was to be able to achieve a heat shield that would be able to withstand these incredible temperatures. And so this is a look at our thermal protection system, our TPS, as we call it. So at closest approach, the heat shield is about 1,400 degrees Celsius or 2,500 degrees Fahrenheit. But the payload itself that sits on the main body of the spacecraft is a little bit above room temperature. It's it's a Nicky room temperature. It's about 78 degrees. I'm always cold. But so for me, that's room temperature. But it's extremely, extremely important for us to be able to have a heat shield that will actually be able to withstand these temperatures and also be light and compact to be able to launch and be sturdy enough to withstand 24 orbits. And so one of the things that if you haven't seen our mission design, we actually we do very big sort of petal-like orbits. So we go very close to the sun on one side and we come out around the orbit of Venus on the other, which means our temperature changes dramatically. We go from like the cold of space into the heat of the corona, and we do it 24 times. So if you think of taking any material that you know and heating it and cooling it continually, most materials will change their properties. They'll either become brittle or they'll become elastic and deform. And so this cannot do either. It has to remain and be able to withstand these huge changes in temperature. And so the heat shield itself is made of a carbon-carbon, it's a bit like a graphite epoxy that you would find in your golf clubs or a nice bike. And it is 2 phase sheets, very, very thin phase sheets. The whole heat shield itself is about 4.5 inches thick, so about 8 feet in diameter. We call it our 8-foot frisbee. And it is these two phase sheets, and then in between those is a carbon-carbon foam, which has the texture a bit like forest foam that you might get flowers in. It has that kind of texture, so it needs to be handled very, very carefully. You'll see a video of us kind of putting these together. And then on the top, we have a special coating that actually reflects most of the sunlight. The other challenge we had was actually kind of holding the heat shield in place. And so in the middle there, you see our truss structure. And that was a piece of engineering marvel of itself. It is a titanium welded structure, and it was produced for us by one company was brave enough to actually say they wanted to do it. We put out bids for all over the place, and one company said, okay, we'll have a go. And so they were actually, had been doing welding for nuclear, mostly submarines. And so this was the first time they'd ever done space. And so it was a wonderful thing where we had their 3 best welders were the only 3 people that worked on this. They wouldn't let anyone else touch it. They were very, very proud of it. And they actually came to deliver the structure to the Applied Physics Lab right before we installed it. And it is an incredible marvel. It is light. It is incredibly, incredibly strong. And it is very, very sturdy. So it can withstand all kinds of torque as it's moving around on the orbit. The other thing is that we have to attach the heat shield with the minimum number of attach points because you don't want any heat convecting into the system. So the whole thing is held on with only 6 carbon bolts. And not only is that a challenge, but as we're going through all these different heat changes, the whole heat shield kind of bows like a drum and potato chips and moves around. And so the whole thing is on kind of like shoulder joints so that as it moves, well, this is the plan anyway, as it moves, the heat shield can kind of move around and these joints will hold it in place. So a huge, huge amount of technology just in this one piece. In the very top, on the right-hand side there, you see some sort of black fin-like structures that are mounted on this truss. So not only is this assembly holding the heat shield in place, but it is also where we put our radiators. So those are the radiators you'll see later that actually get rid of all the heat that we generate in the solar panels. And so this is a dual, multi-purpose object that we had to create for Parker Solar Probe. And so here's just a nice demonstration. This is just a small test sheet of our heat shield. So this is obviously the front side where Betsy is heating it with a blowtorch and getting it really, really hot. And now you will see Curtis come in and put his hand on the other side of it, and it is nice and cool. And it really does work. I've done it several times. So one side is glowing red, and you cannot feel any perceptible heat on the other side. Very similar to a shuttle tile, actually. All right, so here's a nice shot of our whiter than white coating, as we call it. So that is an alumina coating. It is plasma sprayed onto the front of the heat shield. And the reason that we have this is it actually reflects most of the heat from the sunlight, so we don't even have to deal with it. So when we talk about the plasma in the corona, we say it's 3 million degrees, and you're probably wondering why, if we're in 3 million degree plasma, the front of the heat shield is only, you can imagine how much the engineers like it when I say only 2,500 degrees Fahrenheit. But because the plasma itself is not very dense at all, there are not that many particles, so very little of that actually couples into so it's a bit like the difference in heat and temperature. So if you put your oven on to 500 degrees, you can put your hand inside your oven and you will not get burned unless you touch a surface. When you touch a surface, you've coupled and you're allowing the heat to now burn you. But if you just put your hand in the environment, there aren't that many particles. And so even though you feel heat, you don't feel the 500 degree heat that your oven is currently at. And so that's pretty much what Parker Solar Probe is going through. Very hot plasma, but not that many particles. However, the sunlight is incredibly strong when you're that close to the sun, and so it's really the heat from the sun that we have to worry about. And so we put this white coating on, which enables us to reflect a large amount of the sun's heat directly. And so it's a little bit like the difference in being in a black car on a hot day or a white car on a hot day. Much, much better off in the white than the black. One of the other challenges that we had was using solar cells. So the Parker Solar Probe, or the Solar Probe mission concept, has been around for 60 years. There have been many different incarnations of the mission. Most of them involved using RTGs or some kind of nuclear power system. The initial thought was to make it kind of like a cone shape, and so it looked a little bit like a bullet. Fly it out around, do a gravity assist around Jupiter, come up out of the ecliptic, and then go sort of north-south past the sun very close. That was an incredibly expensive mission, and it took a long time to be able to achieve 2 flybys. And so the budget for heliophysics, or Sun-Earth connections as it was at the time, was not large enough to be able to do this mission. And so NASA came to the Applied Physics Lab with a challenge, which was to do a much cheaper mission and not use nuclear propulsion, nuclear power, sorry. And so that meant that we had to change. We changed the orbit completely. We now stay in the ecliptic, so we don't move out and do a north-south. We're in the same plane as the Sun-Earth line. And we use Venus to fly by. So we use solar panels. And so you think, that's easy. You're going to the sun. Solar panels. Awesome. Except everybody knows what happens if you leave your iPhone on the front seat of a car on a hot day. Like anything, electronics and solar cells in particular are not efficient when they overheat. And so now we have a challenge of being able to keep our solar cells cool. And we do that using 2 different methods. The first one is that it's actually a very unique design. We have liquid-cooled solar arrays. And so we use water to cool them, because even though I know everybody's thinking, really, all this technology, and she's using water. Water turned out to be the most efficient fluid to cool. And so what you look at here, you can see a couple of different views of our solar cells. In the picture of the spacecraft in the middle, you can see it's got the whole array out, and at the very end, you can see a sort of a silvery-looking piece. That is the piece that you're seeing inside the heliostat vacuum chamber there. So that is the very edge of the solar cell. When we are out around Venus and close to the Earth in the cold part of the orbit, they are all the way out facing the sun to get the maximum amount of solar power on those cells. As we move in and we come in, they tuck in until just that last row, the tiny row of cells on the very top there, is the only piece that is illuminated. And just that one row of cells, because we're so close to the sun, will produce the same amount of power as the full wing does out around Venus. In between each of those solar cells, there are like veins, just like you have veins that run through your hands with the blood that will radiate and keep you cool on a hot day. We have water that flows in between each of those cells. It is actively cooled. We have a collector inside the spacecraft where the water is stored and continually loops around. And then those radiators that are housed on that truss structure are what actually gets rid of the heat from the water. So here we are. This is installing and testing the solar panels. And so you see we tested them with a purple laser. And the reason that we tested them with the purple laser is that they actually, it's very easy to see with a laser. You can get it incredibly, incredibly fine. And we can actually illuminate one cell at a time with the laser. Using these purpley blue colors makes it extremely easy to see. The cells respond and are very efficient with that color. The laser itself is not enough to actually power the spacecraft, and so we actually used infrared, but of course you can't see that with your naked eye. So if I showed you the movie of us doing it with infrared, it would be really boring because you can't see anything. But that was our purple light test where we verified that each one of those solar cells, indeed there are 44 cells in each array, and that each one of those was still working. And so here's just a view of solar probe on orbit, and you'll see when we're out around Venus, those solar panels are all the way out, and then as we get close to the sun, they move all the way in, tucking away so that we don't get too much heat. Because of course, any heat that we generate, we have to get rid of. So we want to generate as little heat as possible. And so the next sequence is, it's going to go pretty quickly. It's a sort of time-lapse video of us building the spacecraft with some highlights that I'll try and talk through. So the first thing you'll see is us putting together the actual primary structure. And again, I think this gives you an idea of how small the spacecraft is when you see people standing next to it. So here's that harness I was talking about. It's going to go in around the propulsion tank. Here is the top deck, and so this is when Parker Solar Probe finally started to look like herself, when we put that top deck on. This is, so you see there's a phase sheet, and they're bonding that foam piece to the center of it, and then this is our heat shield engineer making sure everything's working fine. This, at the time, was the most terrifying thing I'd ever seen. It was the vibration test for Parker Solar Probe. This then became the most terrifying thing I've ever seen when we lifted her 4 stories in the air and put her inside a vacuum chamber. So that was at Goddard Space Flight Center, where we did most of our environmental testing. We flew her down to Kennedy on a C-17, courtesy of the Air Force, and I actually got to fly with her, which was awesome. Here we are putting on the solar panels. The solar panels were put on just to make sure that they didn't get damaged during the flight. This is just one of my favorite things. This is the stand that this thing lets you move the spacecraft to any orientation that you need to be able to work and spin it around, and it's a wonderful piece of technology. I'll talk about this a little bit more. Several of you may have either had family members that did it for you or put your own name on the spacecraft. This is testing the magnetometer boom, so you'll see a sequence in a minute where you see the instruments come out, but that is obviously stowed for launch and then stretched out when we get on orbit. There's putting on the, so you see there was a little shot there, you could see that sort of shoulder joint coming down as the heat shield was installed on the spacecraft. Here we are lifting the spacecraft, yet another terrifying sight, and there she is sitting inside a 40-foot fairing on top of our upper stage, and the next stop, of course, was launch. So a couple of things from that. So you may have noticed that the heat shield was the last thing to go onto the spacecraft. So the heat shield went through its own testing. It completely separate from the spacecraft. The only thing we did was when we did the vibration test, we had the heat shield on. But of course, the heat shield has a totally different environment that it works in. It has to be able to withstand these huge temperature changes. But it is shading the rest of the spacecraft, so the rest of the spacecraft does not have to go through. And in fact, we do not want the spacecraft to go through that kind of environmental testing. So the heat shield itself went through its own test program, and then they met up at Kennedy. You saw the spacecraft coming down in the luxury accommodation of a C-17. The heat shield came down by truck. So, but they met up there, and we installed them. Okay, so there is an extremely beautiful sight of our Delta IV Heavy right before launch. The bright star that you can see, or the bright, it's actually a planet, it's Venus. And so it's extremely poetic for us that right before we launched her first stop is Venus, and there was Venus out for us to see. So a beautiful, beautiful, balmy, sticky August evening in Florida. And here is the launch. So our Delta IV Heavy lifting off the pad, truly, truly spectacular launch. I know a couple of you were at the launch, and it was an amazing, amazing sight. But there is our Delta IV Heavy lifting off. I still get chills when I watch it. I do. So at least I'm not crying this time. All right, so there is. So now we go to an artist's impression of the fairing opening on orbit and Parker Solar Probe coming out. We had a cryogenically fueled second stage, which you'll see separating now. And then we had that upper stage, that kick motor that gave us our final, in fact, it gave us more than half of the launch energy. It was about 75% that came from that upper stage. Parker now on orbit, putting out the solar panels, the first thing we always do to get power. Then we want to deploy anything that is stowed. So the magnetometer boom is a pretty big boom. You saw it walking out during the testing. It's actually a pretty big thing. So we wanted to get that out as soon as possible. And there are the electric field antennas. And so just about 7 weeks after launch, Parker Solar Probe encountered the planet Venus for the first time. She did a gravity assist around there. Now, we're very generous with this mission. We give energy to the planet. We don't take it like those planetary missions. So we actually we use Venus to slow down just a little bit. I like to say it's a bit like doing a handbrake turn, so that we turn closer and focus our way into the sun. And there is Parker Solar Probe tucking those solar panels in, ready to make the first closest approach of the sun. We do this 24 times. We fly past the planet Venus 7 times during those 24 orbits. And so we basically have like 7 little mini different mission configurations as we gradually get that orbit to go smaller and smaller until we're very close to the sun. And so this is just a nice graphic of, you see Parker Solar Probe in the blue. There is Venus, so as we fly past Venus, and you can see how the orbit kind of just tucks in a little bit more. And so when we come out on our aphelion, or the furthest away point, we're now well inside where we launched from. So if you can imagine doing that 7 times, we'll continually shrink that orbit. And so we are not competitive at all. We're just faster, hotter, and closer than anything else. And so we are hotter. Clearly, we're in 3 million degree plasma. And we have to take those very big temperatures. We are moving faster. So we've already broken the speed record. We broke it on the first orbit. But as we get closer and closer, the spacecraft will move faster and faster. And at our final closest approach, we're moving at a blistering 430,000 miles an hour, which is about 118 miles a second. And even I couldn't do that in my Z3. So I had the tickets to prove it. And so closer. So how close are we going to get? I keep saying that we're going to be really close. So we're going to be within 3.7 million miles of the sun. If I put the sun and the Earth on a football field, and I love the way it actually says it's not to scale like you actually thought it would be. So Venus is on the Earth's 28-yard line, Mercury on the sun's 35-yard line. Those really long coronal loops can actually extend out to about the 15-yard line. So up until very recently, Helios 2 was the object that had come closest to the sun. And Helios 2 got as far as the sun's 29-yard line. Now, if we bring Parker Solar Probe, the newest mission to study the sun, into the main event, she will tuck and run all the way to the sun's 4-yard line. So well in the red zone, knocking on the door for a touchdown. And so, you know, but when I say to people it's like 3.7 million miles, and they go, oh, I thought you said you were going close. But, you know, you have to think of the celestial scales of the 93 million miles between the Earth and the sun. And so that really is incredibly close. And it does show why we needed to do all of these technology developments to be able to get there. And so here's, because I love this movie, here is just yet another look at Parker Solar Probe in all her glory, flying past the sun. Nice and close. And there she is. And so you see the whiter than white coating on the front of the heat shield. You see the electric field antennas. And then most of the instruments are in the main body of the spacecraft, staying nice and cool. And so obviously I've said, I talked a little bit about the Send Your Name to the Sun. So there is a plaque that is on the spacecraft, and it houses a small chip that holds the over a million names. Who put their name on the spacecraft? Yay, excellent. Who had it put on for them by their mum? All right. So also on there, of course, is an inscription from Gene Parker. We also have some photographs of Gene. We have his 1958 paper that actually inspired the mission. And so there's a lot of history on there. But that card was installed onto the spacecraft and is flying with it. And so, you know, the exciting thing for us, of course, is this is the first time that NASA's ever named a mission after somebody during their own lifetime. And so it was a great honor to be able to stand with Gene and watch him, sort of watch his legacy lift up to go into space. And I was at some, you know, I leant down and I said, hey, Gene, how does it feel? And he sort of looked at me very quietly and he said, we did it. Woohoo! And I think the woohoo was there because I think he felt that he hadn't emoted enough, but he was so moved by what was happening. And it was just, it was an amazing thing for us to have. And the whole time that we worked with Gene for really the last year up to the launch, he gave so much credit and so much just kudos to all of the people that had made the mission happen, all of the engineers. And so about probably October of last year, I actually got to take Gene into the clean room at the Applied Physics Lab and show him the spacecraft. And so, yes, I did say Parker meet Parker. What else? And so, you know, it was just wonderful watching him just look at this engineering marvel. And, you know, he turned to me and he said, you know, all I did was write a paper. And I said, yeah, it's a pretty good paper though, Gene, really. And so he said, yeah, but if it turns out that you get there with this mission and I'm wrong, I'll just write another paper. He said, but if you get there and your engineering calculations are wrong, that's a whole different thing. And so he said, you know, that the actual brilliance of the technology and the engineering that went into this mission was quite staggering. And so he was, for all of the engineers that lined up to shake his hand and say what an honor it was, he kept saying, no, no, really, this is all you. And so there is just, this is like 4:30 in the morning. He was really good as I was fangirling all over him. But, and I'm absolutely sure at 4:30 in the morning, the last thing he wanted to do was take a selfie. But he did indeed let me do that. And they actually brought with them a brewery where his son lives had actually made a special batch of beer. It is called Parker Pale Ale. And, oh no, is it Parker? No, I'm not good. No. It's definitely pale. Parker Solar Pale, that's right, PSP. So, and it was made with Galaxy hops. Mm-hmm. And Gene actually went to the brewery with his son and stirred the hops. And so they sent down for the launch a little growler full of this beer. And again, at 4:30 in the morning, the last thing I wanted to do was drink this beer, but we all stood together and cheersed the mission with this very nice Parker Ale. And so that is right after that. All right, so let's talk a little bit about the mission. So she's up and she is working. She has completed her first orbit. And so you can see up in that little green line there, she's passing through the orbit of Venus again around now, and then is moving in to make her second closest approach in April. We're actually very delighted. We're getting down about twice as much data as we thought we would. This is the wonderful thing about when you build conservatism and margin into missions, and then when you get up there and you realize they actually perform better than you'd even hoped. And so we're going to get about twice as much data down as we had originally planned, which is very exciting. You can see, if you look at the sort of the wiggly line plot, you see where the green one is, that's where we are. But you also notice how that orbit is shrinking. It's a good way to see how that orbit gets smaller. So right before each kind of compression, we've done a Venus flyby. And so you see how we're walking closer and closer. So this is, oops. Oh, come on. Ah, there we go. All right, so this is the look at the spacecraft, so you can actually learn something about the instruments. So this is what we call the anti-ram view. And so Parker Solar Probe is essentially moving sideways when she skates past the sun, because that heat shield has to stay between us and the sun all the time. So it's kind of a bit like fishtailing on an icy road. But we have, so you see the thermal protection system, the heat shield out in the front, and those solar arrays at the back there moving in and out. They're also, by the way, on shoulder joints, so as they come out, they can also sort of flap and feather to maximize or minimize the amount of sunlight they're actually seeing. Our high gain antenna up there is extremely important. That's how we get all of our data back. It also is quite a challenge for us because there are a lot of times where the heat shield is actually blocking our view to the high gain antenna. And so we have to do like a sort of store and dump. We carry enough memory to be able to put at least 2 orbits worth of data on the spacecraft. And then whenever we can see it, we will download the data. Because of some margin that we discovered with our radio frequency, the RF margins were very healthy. I'll put it like that. They were very conservative. And so we've been able to lower those margins. And so for those of you who are into data downlinking, we were able to change some of our passes from X-band to Ka band. And the reason that is important is X-band is a very slow moving signal. So we were basically using that for commanding and downlinking emergency data. by going to a Ka band, we are able to really, it's about 4 or 5 times the rates that we can get the data down, and that's what we use to bring down the science data. So now we have a lot more Ka band passes than we thought, and so all these data are coming down. Actually today, they're downlinking data. Let's see, you can see the electric field antennas, but you also see the sweep SPC. So that is a Faraday cup, the solar probe cup. And I always like to think of that as the bravest little instrument on the spacecraft, because while everybody else hides in the shade, SPC looks around the heat shield. It was a huge challenge to do that instrument. It is a Faraday cup, and for those of you familiar with space instruments, Faraday cup was one of the first instruments to ever fly. It's an extremely simple instrument, except when you need it to operate at 2,500 degrees Fahrenheit. And so finding materials, again, that would be able to withstand these changes. At first we thought, well, tungsten will do it. Tungsten's a great thing. It will withstand huge temperatures. But the big variations on the outside meant that tungsten was not going to do it for us. And so it's made of very exotic materials. Apparently, the longer the name, the more expensive it is. But we have things like molybdenum and molybdenum and all kinds of other things that we use. There is sapphire crystals that are inside there. Anything that we could do to make sure that it would withstand these temperatures. Obviously, you know, the fields team always gets upset with me because they say, you know, our antennas are out there too, but they're very, very thin tubes of niobium, whereas SPC is a big honking instrument. And so that is one side of the spacecraft. If we flip it over and we look at the ram-facing view, so this is the sort of the leading edge as we skate past the sun, you can see the 4 fields antenna. They are our electric field antenna, and they also measure our plasma waves. You can see WISPR. That is our white light imager. It is a camera that is taking images basically of what the spacecraft is about to plow through. And so it's not taking the solar images that we're used to seeing, but it is taking the images of the solar wind that we're about to fly through. I should have pointed out on the other side of the spacecraft, there was span B, and when we flip it over, you can see span A+. Those are basically sister instruments. They have fields of view that fit together like the seams on a baseball. And so it gives us a 360-degree view of the electron population in the solar wind. It's extremely important for us to be able to see that full distribution, because when we are close to the sun and we're on closed field lines, we would expect to see electrons moving in both directions. And so we have to have, it's incredibly important to have that ability to look at 360 degrees. With the field's magnetometer boom, you saw that one coming out when we first deployed the spacecraft. There are 3 magnetometers on there. The reason we have 3 is because we know the fields will be very dynamic, and so we need to cover a huge frequency range, and 1 magnetometer is not going to do that for you. So we have a search coil magnetometer on the very end, and then 2 almost identical flux gates that are sort of in the middle region of the boom. The reason we have 2 is we have one that is really sampling what the spacecraft is doing, and we use that to subtract it from the outer one to make sure that that outer signal is as pure as possible. And so between the outer flux gate and the search coil magnetometer, we cover the full frequency range that we expect to see in the corona. And then lastly, we have the ESA suite, and that is our high energy particle detector. So the sweep suite is basically taking kind of the bulk plasma, what is continually flowing in the solar wind. It measures the speed, it measures the density and the temperature of all of the particles that really make up the solar wind. The ESA suite is looking for transients, so things that are associated with shocks, with flares, with coronal mass ejections. It's kind of, if you think about the solar wind as the ocean moving smoothly along, and then the high energy particles are kind of a speedboat moving across the top of it, kind of skating across the solar wind. Much different energies, different types of particles, and so that's why we have so many instruments on the spacecraft. So this is our first light image. Unfortunately, I can't show you a lot of, I do have data, but I can't show it to you because it's all embargoed right now. But this is our first light image that was taken by the WISPR camera. The WISPR is essentially a coronagraph. We make sure that we don't look at like you're familiar with seeing coronagraph images, you use an artificial disk to block out the light of the sun so you can see the hazy atmosphere around it. This is essentially like a coronagraph. We use a baffle to block out the sun, and then it looks very close to the sun. Right now it's looking at about 0.1 AU, so it would be about the 10-yard line on the football field right now is where it's looking. But that is the Milky Way. you can see there, and that is the highest resolution of the Milky Way ever taken with a coronagraph, if that record means anything. And then you can see a couple of planets. You can see Venus and Jupiter in the bright spots there. So that is the first light image from WISPR. And then the next, it's kind of a reveal plot I really like. It's data taken during the commissioning period of the Faraday Cup. And the reason that it is interesting is as this goes across, the spacecraft was pointing in an orientation, so it wasn't looking directly at the solar wind, it was looking off to the side. So we did not expect to see anything particularly interesting, just some background data. However, as with all great scientific instruments, something exciting happened. We don't know what it is yet, but here it is. So that red line should not be there. We're not looking directly at the sun at all. So with some kind of structure moving in a direction that we were not expecting to see already being detected by the Faraday Cup. And so that was our sort of quick look data during commissioning. A nice shot there also you can see of the spacecraft in her 40-foot fairing on top of a Delta IV Heavy. She looked like a hood ornament. All right, so that is Parker Solar Probe. But why do we do this? So we go back to the sun. The sun is so central to us. It causes our space weather. It causes beautiful northern and southern lights. And so whenever we see the northern and southern lights, we know that there are currents flowing in the sky, and they can, of course, interfere with our technology. And there are multiple different aspects of space weather that we have to worry about. We worry about safety to our spacecraft, single event upsets, spacecraft charging events, damage to solar panels, damage to electronics caused by these high energy particles coming in, airline traffic, airlines that have to avoid the polar routes when we see large polar cap absorption events, large radio signals coming from the sun. Astronaut safety, of course, a big issue for us, making sure that we don't put an astronaut out on an EVA during a large period of space weather activity. And of course, those power grids underneath the aurora. You don't have to worry about it so much here because I'm guessing you don't see too many aurora. But when I was in Michigan on Monday, they're much more worried about it up there. But wherever the aurora is flowing, you have a current system flowing above you, and it will interfere with a power grid, an undersea cable, a long pipeline. And so there are many reasons that we care about space weather. We care about being able to look after our technology. Parker Solar Probe, of course, will make transformational improvements in our ability to predict what's happening. We'll finally have these measurements inside the inner corona, explaining why the solar wind behaves as it does and how it changes, how it is driven, what is really causing it to act the way it does. And so when we can add the physics into those models, it will make a dramatic difference in our ability to predict what is happening here at Earth. And so, of course, I would be remiss if I didn't talk about all the rest of my children. So Parker Solar Probe may be the new baby, but we have an awful lot of active missions in the portfolio for heliophysics. And so we have missions that obviously are looking at the sun. We have the Solar Dynamics Observatory. We have Hinode. We have SOHO that is still the workhorse providing our coronagraph images stereo. We are hoping next year that Solar Orbiter will launch. That is a NASA ESA partnership that is going to go out of the ecliptic. And so while Parker Solar Probe is taking all of these sort of in situ measurements in the corona, they will be sitting above and sort of looking with remote sensing instruments at all of the different ways of looking at the sun while we're flying past. So we're very excited for that. We have ACE and WIND that are out in the solar wind, giving us our upstream warnings of what is about to hit the Earth. And then we have a whole host of missions that are in the magnetosphere and in the ionosphere. I have to mention MMS because Pat is sitting right in front of me. But MMS and THEMIS really providing a lot of information about what is driving and powering the aurora. The Van Allen probes in the radiation belts, they are actually undergoing their final throes of their mission right now. We've just done the maneuvers so that they will go into an orbit where they'll actually be disposed on orbit. So they do have to decay. We don't leave space debris. And so we've done that. We're doing the final maneuvers to put them in their last orbit. Of course, being NASA, we will wring every bit of science out of that mission before it dies. And so we're actually excited because we're in a new region. We're in a region that spacecraft don't normally fly through. The Van Allen probes have been living and working in the radiation belts for 6.5 years. And so it was a 2-year mission. And so we're extremely proud of the fact that, in fact, there's nothing wrong with the spacecraft. It's only that we have to use the fuel to put them in a de-orbit, do a de-orbit burn for them. Otherwise, they would go for many more years yet. But they have had many discoveries, and we will continue to take great science with them. And then one of our new members to the fleet is Gold. It was the first time that NASA put a science instrument on a commercial spacecraft. And so that was a bit of a trailblazer for us. We're hoping very soon that ICON will be launched. These missions in partnership are looking at this sort of new region that we've discovered that is very interesting, where the space weather from above is mixing with terrestrial weather from below. And in this region that we didn't really think anything terribly exciting was happening, but we now know that there's a lot of really interesting physics that's going on there. So ICON is taking images of this region. Gold is taking images of this region while ICON is flying through it. And so we're very excited about that partnership. We just also selected a mission of opportunity, which is called OR, and that is also looking at this region. So this threesome is going to do tremendous work to be able to explain this new region for us. And then, of course, not only do we have all these missions, but we have this incredible mission called Voyager. And Voyager is 41 years old. So after Voyager did this amazing tour of the solar system, flying past all of the major planets and doing a tremendous, finding out all kinds of amazing things about our outer solar system, once it was sort of out and about, it got turned over to the heliophysics division because it was in our very outer region. We're also working on a new mission called IMAP that is going to image what our heliopause looks like. So this kind of boundary that protects, we're in this sort of protective bubble, and it's all driven by the solar wind. So everything is driven by the sun, even the very edge of our bubble in space. It kind of breathes as the solar cycle changes, our whole heliosphere changes. And of course, we were very happy that last November we could say, ladies and gentlemen, the Voyagers have left the heliosphere. And so they have crossed the heliopause and they're out in interplanetary space. And so now, instead of just being everything the light touches, I am now to the heliopause and beyond. So, but it was a big science result for us again. 41 years old, these spacecraft are still working beautifully. And so, that leads me to sort of my concluding remarks, which is really, what next? And so what are we going to do next? NASA has done so many amazing missions. Here you see a sort of artist's impression of what our bubble in space, this is our protective cocoon in which our solar system resides. And how are we going to further explain what is going on? Everything starts from the sun. It powers everything in our solar system. 99.9% of the mass of our solar system is in our star. And so how are we going to continue? Are we going to provide a mission that will actually kind of rocket away from the Earth and achieve interplanetary space much quicker than 40 years, like an interstellar probe? Are we going to do something where we continue to look at the heart of the sun, maybe going over the poles, maybe continuing to try and unlock the mysteries? And so I would say that whatever NASA does is inspirational. We have been to every major planet. We've been out to Pluto and beyond. We've even now left the heliosphere. And so, I think that I hope you continue to join us on our journey as we move out and beyond. Oops. There we go. So everything I think that NASA does is truly inspirational. And I hope that you agree that Parker Solar Probe is a very inspirational mission. It's taken 60 years. It has never wavered really in support. Everybody always knew it was the next big mission, but we've had to wait for these incredible technologies. And so I invite you to continue to follow NASA with me, continue to be inspired, and to continue looking up. Thank you.
Okay, so this is where I earn my glass of water. Questions, please. I'm sorry, I don't have the handheld. You're going to have to use this one.
So I have a couple of wake questions, right? So the first wake question is about the heliopause wake. Did the Voyagers go out sort of in the direction of in the direction that the Earth, Sun is moving through the galaxy, and so that,
They went
can
out
you
the
talk a
shortcut.
little bit?
They took the shortcut out.
They went out the front end.
So in the same way as you see our magnetosphere, and it's sort of compressed on one side and then a long tail on the back, our whole heliosphere looks like that. And so as we move through, it's sort of compressed at the front, and then it moves out into a long tail behind, a bit like a windsock. And so, yes, the Voyagers did go, I jokingly say they took the shortcut, but they did go out the front. They went out of very different regions of space, it's almost like one's north and one's south. They're in very, very different regions that they cross through, which is already giving us a lot of science just from how they look different. So they're kind of in the sheath region now. They're not fully, they are in interplanetary space, but they're still in a region that is still feeling the impact. It is like a wake, a bit like a bow wave at the front of the boat. So they're kind of in that region right now. Voyager 1 has been out for a number of years. Voyager 2 just popped out in November.
All right, second wake question is about the solar probe itself,
yes.
Right? So did they do anything to kind of keep the wake of the solar wind from impinging on the instruments and stuff to sort of, beyond just sticking something out there? Did they think about the wake, and do you know anything about whether they tried to protect particles from bending once they hit the spacecraft and hitting the instruments, or did you experience any of that kind of stuff?
So the easy answer is I want as many particles to hit the instruments as possible, because that's. But do we worry about it? Yes, we do. We did an awful lot of modeling. We have to think about a lot of things. Dust is one. We're going into a very dusty region, and a tiny particle, when you're moving that fast and it's moving fast, is almost a game over. And so yes, we did an awful lot of modeling and predicting of the dust. We shot an awful lot of particles at an awful lot of different detectors to make sure that they would survive. In fact, Whisper, the camera, went through a lot on exactly what they were going to use for their lenses to make sure that they could withstand dust impacts. A bad dust impact, you'll definitely be able to see it, and it will take out some pixels of the camera, but it won't ruin the whole camera. And then radiation shielding, absolutely. Now, the good thing with Parker is all of the electronics really are inside and protected inside the actual shell of the spacecraft. And so it really is only the detectors that are out. But yes, a huge amount of effort. Also, light pressure. That, if you get that wrong, that will flip the spacecraft. And so a tremendous amount. We benefited a lot from what we call pre-phase A money. So those of you associated with NASA missions know all about the phases. But phase A is basically when you start the real design work. And we had a lot of pre-phase A money at the Applied Physics Lab to do an awful lot of this modeling. We had a whole panel of dust experts. We had a whole radiation group. We had people looking at whether or not the heat shield would be conducting. And so, because the actual plasma properties change, the energy of the particles change, the amount that you're seeing changes. And so we had to actually look at, are we going to have a sheath of electrons around the spacecraft when it gets cold? And how do we deal with that? And unfortunately, you actually have to say, well, we've got to protect for when we're enclosed. And so you'll have to deal with the cloud of electrons that will follow the spacecraft when it's cold. But yes, a tremendous amount of modeling went into that. But honestly, the biggest fear was the pressure flipping the spacecraft.
Saw the length of the mission, 6 or 7 years. I take it that the limiting factor was propellant, since you always have to be sun-facing. So with that, you've had an orbit now. Have you used about as much propellant as you expected? You think you might get a longer run out of it? And how will it end? Are you going to run it into the sun, or will you have enough energy left for that?
Okay, so actually it's kind of a good news story. She said knocking on wood, but it is kind of a good news story. So one of the things I didn't mention was ULA with their Delta IV Heavy put us smack dab down where we needed to go. They were, I don't know how many, it's fraction of you know, where we actually are perfect trajectory, which meant that we did not need to use hardly any fuel to do the correction maneuvers early. And they were the big ones. And so we actually have canceled a couple of our correction maneuvers because we just didn't need to do them. And we actually think, you know, yes, you are right. So there's a couple of pieces. Yes, you're right. Fuel is our limiting factor. Once we run out of fuel, we can't keep the spacecraft oriented. But we do believe that we'll have a lot more margin than we thought we had, because we didn't need to use all this fuel early in the mission to do those big maneuvers to make sure that we were going to go to the sun. And so 7 years is our prime mission, and that is based on getting us into below 10 solar radii, or within that 3.7 million miles. We think we've got a lot more orbits after that. I had to be really careful because now I work for the other side. I can't like make promises about how long it'll be funded. But yes, there's a lot more life in the old girl yet. So she will continue well beyond the 24 orbits. One thing I didn't mention actually is we use momentum wheels largely for attitude control. And that was a decision early on. And it was a big hit for us with the mass. Because they actually weigh a lot. And they take up a lot of real estate in the bottom of the spacecraft, too. We were going to do everything with thrusters. But then it became very clear, very quickly, that we would never get any electric field plasma and plasma wave measurements, because all we would be measuring would be the puffs of gas, and that they would be going all the time. And so we very early on took the hit and went to the momentum wheels. So in the first flyby, we were expecting that we might have to do a couple of momentum dumps. So when they get sort of spun up and you have to de-spin them. And we thought we would probably be doing up to 1 or 2 a day. We did 1 in the entire 11-day flyby. And so that helps too, because the less I have to puff those thrusters, the longer I can keep the mission going. And so I'm cautiously optimistic, shall we say, yes.
And I think the last part of Wood's question too is when it's done, it's just going to be in its,
I'm sorry, yes,
its orbit.
Yeah. Yes, so after the 7th Venus flyby, that orbit is completely stable. It will just continue in that orbit. We are too close inside Venus at that point to do another Venus flyby. I'm always getting the question, well, why don't you just do another one and go closer? But we're actually we're sort of inside it at that point, so we don't get enough momentum to be able to do that. But no, that last orbit will just stay, and then, you know, I know the question is what happens when you run out of fuel, and it's the question I hate the most. But at that point, the spacecraft will start to turn because we won't be able to keep the heat shield anymore, and so bits of the spacecraft that are not supposed to see the sun will see it. And so it will break up, first of all, into large pieces, and then it will get smaller and smaller until she becomes part of the dust cloud and orbits the sun forever. But my heat shield engineer tells me the heat shield will survive and will go forever in that orbit. So there's nothing touching that one.
Dr. Fox,
Yeah.
Thank you very much for your wonderful lecture, and congratulations to you and the whole NASA team for this wonderful, wonderful success.
Thank you.
Looking out way into the future, does NASA and does your department consider conceptualizing and implementing a Dyson sphere with respect to putting something that will harvest the energy of the sun and project it back to Earth? And if so, is that in the future somewhere in your concepts?
So I don't think it's probably not in my lifetime, but I think as we continue to look at putting a human presence further away from, outside Earth orbit. Mars is clearly the next target, but what do we do beyond that? If you talk to Jeff Bezos, he will tell you his number one goal is a planetary home off this world, so that human race will continue to survive. And so there are things that you have to think about. How would you get power if you went to another solar system? Where do you do that from? How would you do that? And so I love the Dyson sphere. That's a great thing. But I wonder what you meant at first, and then I got it. But I think it's something we need to be thinking about. There's also mining asteroids. There's many different branches. And honestly, what sounds like science fiction today isn't tomorrow. I mean, if I said to you, even probably 20 years ago, we're going to do this mission, you'd say, and you're crazy. So, I don't think anything is beyond the realm. Do I have plans to do it right now? No, but it would be nice if we could.
The Japanese have got a concept of ringing the moon, not covering the moon, but ringing the moon with solar panels.
Yeah.
To generate energy to beam back to the Earth. You have to make sure that microwave hits the right place.
Yes, yes.
Thank you. Thank you for coming out, and thank you, David. You always bring amazing lectures. And with oh my gosh, this was one of the best. It really was. And I've seen a number of them here. My question has to do with neutrinos. So obviously, there's a lot of neutrinos coming off the sun. My understanding that, through every square centimeter of your body right here on Earth, there's like 65 billion going through every second. And I'm guessing if you half the distance, it's twice as many. Mm-hmm. And anyway, where I'm going with this is, I'm curious if, I noticed you had a picture of the Milky Way. And I'm guessing it was taken from the solar probe, okay?
It was taken with the Whisper camera.
Right, and now knowing that you also have, links to Voyager and so forth, mm-hmm. I was curious, I've often been curious how light has a, what do you call it, the redshifting effect mm-hmm. on, if neutrinos streaming from the sun might have a redshifting effect. And I've often thought that if you could take a picture of a distant galaxy, from one vantage point, maybe the solar probe, and then mm-hmm. compare it to a picture of that same galaxy, mm-hmm. From a Voyager or something, if there would be a difference in the observed redshifting effect, if those cameras have the capability to do such a thing.
So the Whisper camera would not have that. I mean, I showed you that, but it really is a coronagraph, and so it is designed to look at the solar wind, and it's looking for really transients in the solar wind. So, we know there's so much amazing data, and if any of you went to the American Geophysical Union, they showed some of the first data, and there were like audible gasps in the audience at those beautiful wiggly line plots, because so we get excited about our wiggly lines. So Whisper would not be the camera to do it. But something that absolutely, if you have something like where Voyager is and you're comparing it with a high resolution, you would be able to see that. I mean, we're not moving fast enough. We're about half, but Whisper's not going to be that camera. Yes, I should have said that was actually from our spacecraft. And I'll tell you a slightly funny story, which was we absolutely freaked out the principal investigator of that camera, because he didn't realize that when we first launched, we weren't looking at the sun directly. And so, because we're out, we're cold, and so we had it turned sideways to warm up some of the instruments and get the solar panels fully illuminated. So it was kind of moving sideways. And also, as we were commissioning the particle instruments, we wanted to try and get solar wind coming into them. And so we put on the Whisper imager, and he took this image and he got it, and he called me and he said, "I think the spacecraft's the wrong way around." He said, because I'm sure we should be looking at something else. And we had to explain to him, no, it's okay. It's supposed to be that way, and you are looking that way. So we also got a really nice image of the Earth as we left with Parker Solar Probe too. So your question is really good, and you would be able to see it if you had the right imager, but Whisper is not that imager, because it's designed to look at these transients in the solar wind. So we do image the edge of the heliosphere. So IBEX was a small explorer that actually has so E&A imaging, so it takes neutrals and sort of, it's very, I'm not sure I totally understand it, but basically it says, I measured this here and that particle came from over there. And so they essentially paint the heliopause. And they've, discovered there's a sort of ribbon structure and there's all this really exciting stuff in it. And so IMAP is the sort of the next mission from that. So building on what IBEX did, it's actually going to go and image the outside of our protective bubble, and then have all these in situ instruments that are sort of measuring the particles as they come in and looking at what's going on in the solar wind, and then seeing what's going on in the outer heliosphere. So we do have image cameras that do that. You really need to talk to the director of astrophysics, because he has really good cameras that can do that. And actually, if you grab yourself, shameless plugging here, but if you grab yourself a NASA science directorate calendar this year, and I've seen a couple on the wall around David's office, but they have the astrophysics images. They have one that's actually an Einstein bridge, and it is they're taking the images, and you can see the way the light is bending, and it forms a ring, and it's just a spectacular image. And so Paul has better toys than I do for that particular thing. Paul Hertz is the astrophysics division director, but if you can find a NASA, I bet Pat's got one. If you can find one, or actually, if you Google it, just Google NASA Science Calendar 2019, and I don't remember which month it is, but there are several astrophysics images. Some of them are layering the different cameras, so from Hubble, with looking at all the different wavelengths and putting a number of these different things together, and just have spectacular pictures of the different galaxies. And so Paul is your guy for that. Shamelessly plugging another division directorate there.
Yeah, the sun's still the best, though.
Sorry? The sun's still the best.
I said the sun's still the best.
I know. Actually, the planetary division director is always teasing me. She says, "So you have everything the sun touches, except for all the planets and the Earth and the Moon. What do you have left?" So.
Hi, Dr. Fox. I'm
Hi.
up here.
Hello.
Hi. I'm a budding heliophysicist, and so I'm on the outside of the field at this point, and I'm curious. I know with a lot of the data that will be coming in from the instruments on PSP and such, it's a lot of particle physics and such, but I'm wondering, just as a whole for the heliophysics fleet, are there any plans to do citizen science with any of the spacecraft? I mean, you've got tons of amazing missions. IRIS had some amazing imagery and things like that. So once the data makes it to the PDS, were you guys thinking of any kind of citizen science type projects?
So we're definitely thinking about it. That's a great question, actually. And we do some citizen science, but it tends to be a little bit more ad hoc right now. So there was an auroral feature called Steve that was discovered, that was a feature well below where people thought the aurora should, like in height, well below it should be. And that was done with citizen science. Juno, the Juno cam, Pat and I were just talking about this earlier today, but that's all done with citizen science. And so NASA's Science Mission Directorate, of which we are one of the divisions, has now a citizen science policy. And so we are looking at ways, but it needs to be good citizen science, with like real science goals. So it's not just somebody saying, "Oh, look, I took these pictures and it's science," but it's really got a focus. And so I would say, give us a few more months, and while we figure out exactly how we're going to roll out the policy. I do have somebody that in my division. Her name is Liz McDonald. You can Google her. She will come up. She has a project called Aurorasaurus. And it is a citizen science thing where you can, if you see an aurora, again, you're in Texas, it kind of sucks, but if you go north, then you might see one. And you can just take pictures and put it in, and they're sort of building up this like real-time network of where the aurora are. But if you're really interested in doing citizen science, Google, she's either Elizabeth, or I'm not sure what she'll come up as if you Google her, but Liz McDonald, and Aurorasaurus, that one will work for you definitely. And she'd be more than happy to talk to you about that. Yes, Pat? She's doing a webcam on Solar Week. Yep. Okay. And so, yeah, she's got lots of great ideas. She loves citizen science, and we're supposed to get together and talk about how we could formalize it for heliophysics. I'm not quite there yet to give you a really crisp answer, but it's something I'm really interested in finding a way to do. Because we have all this data, and so, you saw my fleet, it's just my fleet. It's like it belongs to me, my fleet. You saw the NASA fleet for heliophysics, and you know, we're actually starting an initiative called Whole Helio, which is really aimed at taking every one of those assets and using it together as a system. You know, we have all these beautifully located spacecraft. You have all this modeling that is done from anywhere from the sun all the way down to the mud. And so putting it together in one system, following something and tracking it and seeing how it impacts all the different places, why an event that looks exactly the same on the sun can either cause the radiation belts to pump up, it can cause them to go down, it can cause them to not change at all, and yet your optical signatures look exactly the same on the sun. So what is it that causes the planet to respond differently or the magnetosphere to respond differently? And so, you know, Whole Helio, I would love to have some kind of citizen science in that, because that's an awful lot of data to be looking at for these different events. So there's also something called, I don't remember what it stands for now, but it's WHPI. It's WHPI. And Sarah Gibson from HAO is running a sort of grassroots campaign for us this summer around solar minimum, looking at, again, it's that kind of idea of putting everything together into one system. Yes, that was a really long answer to, I probably just should have said no, shouldn't I? But anyway.
So we have one last question up
Yes.
here. Nikki, please.
Okay, I'll make it real quick. Great program. So I'd really appreciate your coming tonight. My question is, if there was a severe mass ejection or solar storm that hit the spacecraft, could it survive?
Yeah. And so, usually the question is phrased, are you worried that you will see? And my answer is always, I am more worried that I won't see a huge coronal mass ejection, because the sun is really quiet right now. We're at like sunspot number 0 for however many months. But no, we are totally designed for a nice big CME, lots of particles. That's what we're designed for. That's what we want to see. All different kinds of solar wind. And actually, one of the things I didn't mention that makes this mission, again, I'm biased, but that makes this mission maybe better than some of the previous concepts is it is a 7-year mission with, you know, a possible extension, fingers crossed, which means that we're covering more than half of a solar cycle. We've launched in a deep solar minimum, and so hopefully the sun will wake up soon. And we will go through a solar maximum with the prime mission. And so that allows us to see all different types of solar wind. So at solar minimum, you tend to see things that are associated with coronal holes, and so you see a lot of stream interaction regions. As the activity picks up and the sunspots come back, you start to see things that are driven much more by coronal mass ejections, so it tends to be slow solar wind. And so, you know, seeing all of this different type of solar wind is what we really want to do. And so, now, ask me when it actually happens and we're really close to the sun and a honking great CME comes out. Ask me how confident I'm feeling right then. But as soon as I see the data, I'll say, we were fine. That doesn't mean I don't worry about her when she disappears behind the sun. But yes, we're designed for a big CME. Yeah. Like
Thank
to
you.
see one, actually.
And in the Halloween storms of 2003, if you got away from the city lights, you could actually see aurora just outside of Houston. So it does, the sun has a huge effect, and it's even in Texas, right? So
yeah, actually the Bastille event in, what was it, 2000? There were many reports. Actually, it happened. The super big thing happened when you were sunlit, but the auroral oval actually went well down over Texas then, and there were all kinds of radio signals that went wrong in Texas with police radios being heard in cities that they shouldn't be. The ionosphere was very disturbed and strange. So Texas definitely sees the fair share of.
Probably write a book out of those messages, actually.
Yes, yes, March '89. Yeah.
Space weather is really important. Understanding the sun is really important. It's also a star, so we can learn about other things too. And having people like Nikki working where she is, it takes a brave person. Not to build a satellite like this, but to go work at NASA headquarters. So we really appreciate her being there, and just being such a great scientist and being such an ambassador for the kind of science that we're all interested in. So please join me in thanking.
Thank you very much. Thank you. All right.